Alright, we're going to begin section 14.9 in this video, which is parametrized surfaces. So recall that we can use a vector function R of t equals f of ti plus g of tj plus h of tk, where t is between a and b, of a single parameter t to trace out a curve C. So this is just a little recap, and I'm going to relate it to what we're learning. So we would have, we'll call this a t-axis, and we take any point t on there, and we use our vector function r. We'll put t into our vector function r. Then as we take different values of t, and you can sketch any three-dimensional curve you want to. So over here, it doesn't have to look like mine. Then the vector r of t, we need a direction of travel, so let's put some arrows on here. The vector function r of t, as t varies, it would trace out this curve. And this right here, for this particular one, this would be the point x, y, z, where x is f of t, y is g of t, and z is h of t. So just the parametric equations that we're accustomed to. So that would be x, y, z, where x is f of t, y is g of t, and z equals h of t. So this is what we've done in the past, and then in section 12.4, we used these parametrizations to find the arc length of C. So we can parametrize a surface S. And your textbook uses sigma for surfaces, so it looks like the summation symbol. I'm just going to use S. So surface S, in a similar fashion, except we will need two parameters, u and v. where each before I just notice that T is just some real T is just a set of real numbers that we can plug into R, but T doesn't show up in our picture. So the same thing will be the case for when we parameterize surfaces. You don't really see T in here. This is all X, Y, and Z. So two parameters U and V, where each UV is a point in a planar region R. The domain of our vector function R of UV. So now instead of R of T, it's R of UV equals X of UV I plus Y of UV J plus Z of UV K, where UV is in R. And I'll sketch a picture of what's going on here as well. So, and I'll specify the difference between what we're doing here with this parameterization versus when we've been talking about a function f of x, y from like say in 14.4, 14.2 when we were sketching our region R. This is a little bit different than what we were doing there. Our region R there was below, was kind of in the XY plane below whatever our surface was that we were considering. Here we're doing something a little bit different. All right, so now similar to that picture that we had earlier, now our parameters, are they're not in the XY plane, they're in the UV plane. So they don't show up. We don't visually see these. And let's just say you can sketch whatever region R you want to in here, doesn't matter what it looks like. So that's our region R. And if we take some point in there, U comma V, and then we take our vector function and we plug this UV into our vector function R, then what we get is it's going to trace out, our vector function R is going to trace out, instead of tracing out a curve, it's going to trace out an entire surface. So you can sketch whatever surface you want to as well. So I'm just going to keep it very simple. Let's sketch this as our surface. And we'll put some little shading on the surface to indicate we actually have a surface versus just having some curve. And our vector function R so this would be R of UV. You could label it XYZ, but you can also label it R of UV. So sorry, you probably can't see that with my shade, and that just says R of U comma V. So what's happening now is every point UV you plug in to R, it gives you some vector that in the tip of that vector, those vectors are going to trace out this entire surface here. So this is not to be confused with, say, if we were projecting this surface down into the XY plane, the region R that's below that doesn't look anything like this region at all, the region R over here. So before we were talking about surfaces and when we were integrating over surfaces, we might have some region R that's below this, but it was a three-dimensional solid. The surface was just the top of that three-dimensional solid. And then the region R in the XY plane is if we projected a three-dimensional solid down. This is just some surface. It's not a solid. It's not some three-dimensional thing. It's three-dimensional in the sense of that it's in three dimensions, but if we want to talk about its thickness has a negligible thickness. Sorry about that. So there is no thickness to this thing, as though which is in contrast to when we were talking about, say, for instance, a three-dimensional solid region that we would project down into the XY plane. So just keep in mind that we don't really see this in the picture of the surface. That's something completely separate. All right, so now, so this is similar to the parametric equations we had for when we were doing this with a curve C. So we can say where the parametric equations of S are X equals X of UV, Y equals Y of UV, and Z equals Z of UV. So before when we were working with curves, we would call this H, G, F, G, and H. But now we just, to make things easy, just call it X, Y, and Z. And then this is the shorthand of it, just X, or X of UV, Y of UV, and Z of UV. Shorthand is just X, Y, and Z. All right, so let's look at an example. So I'm going to do, because this section is so lengthy, I'm going to bounce back and forth from our notes to the examples versus getting all the notes out the way first. So let's start with number 4 on page 968. All right, I'm sorry about that. Number 4 says, in exercises, sorry, I'm on the wrong page. 14.9, not 14.8. All right, number 4 says, show that R of UV which equals, all right, now I'm going to switch back to not using I, J, and K, which is how you all normally see me writing this stuff. Is cosine U times cosine of V is our I component. Cosine of U times cosine of V. Our J component is cosine of U times sine of V. Cosine of U times sine of V. And our K component is 1 plus sine of U. And say show that R of UV parameterizes a sphere sigma, find the center and radius of sigma. Okay, so what we'll do is, because, and remember I said parametric equations are my favorite type of equations because they're in terms of X, Y, and Z, which we're very familiar with X, Y, and Z. So let's rewrite this in that form. So this is X equals cosine U times cosine of V. Y equals cosine of U times sine of V. And Z equals 1 plus sine of U. All right, so now we were told to show that this is a sphere. So luckily we're very familiar with spheres. So the natural thing for us to do here is look at x squared plus y squared plus z squared and see what we get there. So x squared plus y squared plus z squared equals cosine squared of u times cosine squared of v plus cosine squared of u times sine squared of v plus 1 plus 2 sine u times, not times, plus sine squared of u. Okay, so now if I take and I factor out a cosine squared of u from these first two terms, so that gives us, if I pull out a cosine squared of u from the first two terms and use our favorite trig identity, we'll be left with cosine squared of u times the quantity cosine squared of v plus sine squared of v. So we just end up with cosine squared of u and then plus this. So plus, I'm going to put the sine squared of u right next to this. So I'm going to put this next, plus sine squared of u, and then plus 1 plus 2 times sine of u. So now we can use our favorite trig identity again, and we end up with 1 plus 1 plus 2 times sine of u. So we get 1 plus 1 is 2 plus 2 times sine of u. So we were trying to show this thing as a sphere. So ideally we would have x squared plus y squared plus z squared equals a radius squared. That would be nice. We clearly don't have that thus far. But we still have, the bigger issue is that we still have u swimming around on the right hand side. We're trying to get everything in rectangular coordinates where we're more familiar. So let's see if we can get rid of what we have here. So this is the same as 2 times 1 plus sine of u. And it so happens that 1 plus sine of u is z. All right, so now we don't have any u's anymore. Oops, 2z, sorry, because we have that 2 right there. So now we have x squared plus y squared plus z squared equals 2z. And then from there, you all know from section 11.1 how to take this, bring the 2z over to the left, complete the square on the z's, and then you can find the center and the radius of this sphere. All right, so I'm going to stop this video here, and then in the next video, we'll continue section 14.9.